Hello and welcome to this clip on A2 organic synthesis, which looks at specifically the creation of carbon-carbon single bonds. We look at nitriles as a functional group which extends the carbon chain, acting through nucleophilic substitution or nucleophilic addition. How we can also achieve this in aromatic chemistry using Friedelcrafts alkylation and acetylation, and how both of these reactions fit into more multi-stage organic syntheses of the type you'd be expected to handle at A2. So before going any further, it's worth pointing out that the clip assumes you're comfortable with the majority of first and second year organic chemistry taught in the first roughly 60% of the course. So this means that this clip is best watched when you're towards the end of the course or coming across the idea of creation of carbon-carbon single bonds for the first time. I would imagine around about December, January of your second year would be about the right time. So the nitrile functional group is a carbon triple bond N, sometimes called cyanide. It actually comes as an ion, the C triple bond N minus ion. And the important thing to notice is the R group, which is a organic group of some kind, alkyl chain or arene chain, or ring rather, is bonded to a carbon. So this means that the carbon-carbon bond is created when the C triple bond N functional group is substituted onto another arene or alkyl chain. So you can come across the cyanide ion in a variety of formats in terms of how it's written. You can have the C triple bond N included, or maybe not. But the important thing is that the negative charge rests with the nitrogen and the lone pair rests with the carbon. So it obviously behaves as a nucleophile, but the bonding takes place via the carbon atom when it bonds to something else. This is best explained by having a look at its dot cross diagram. So we start off by allowing plenty of space in the overlap between the orbitals, or in this case the overlap between the shells. And we need to think about how many electrons each individual atom has of its own, first of all. So considering that carbon is in group 4 and nitrogen is in group 5 respectively, carbon has 4 electrons of its own and nitrogen has 5. So seeing as that we've already said that the lone pair exists on the carbon, we have to accordingly put the other 2 electrons within the bond. So we now have taken care of the fact that nitrogen has 5 electrons and carbon has 4 electrons. If we look closely, we'll see that actually, although the carbon's outer shell now has 8 electrons, the nitrogen's electrons shell is only 7. But you'll notice that it's an ion. It's got a negative charge, so therefore the nitrogen must have picked up an electron from somewhere, so the nitrogen carries the negative charge. We draw this in as another shape. So the triangle that I put in there is the gained electron that's responsible for the negative charge that the nitrogen carries. So therefore the nitrogen undergoes a data covalent bond with the carbon, donating 2 of its electrons to a single bond, and then there's also the other 2 bonds making up the complete set of triple bond. So that's how you can justify how the carbon is the atom within the cyanide ion that actually bonds to other things, and in doing so the cyanide ion becomes a nitrile. The resulting compound is called a nitrile. So naming nitriles is really easy. You just use the alkane prefix and then add nitrile to the end. So the examples we've got here, butane nitrile and 2-bromo-propane nitrile. So this other one at the bottom would be ethane nitrile. And you can write it out as CH3CN or CH3C triple bond N. Either way is fine. So when we're carrying out reactions involving nitriles, we have to be very, very aware of the fact that the cyanide ion is highly toxic. This is because it's a competitive inhibitor with the enzymes responsible for respiration, so it blocks the active site of the enzyme responsible for respiration, and therefore in doing so it effectively shuts down all the cells of the body it comes into contact with. So we have to be very careful when creating it, because quite often it's created as HCN, or hydrogen cyanide gas, commonly used in certain states in America as the death penalty, or was used in certain states in America during the death penalty. So it's clearly a very effective poison. So to stop this being a risk, or to minimize the risk, we create the cyanide ion in solution. So using sodium cyanide solution and reacting with the sulfuric acid gives us HCN, or hydrogen cyanide in solution, commonly known as hydrocyanic acid, and then that is also produces Na2SO4. Now the HCN in aqueous solution dissociates slightly into H plus and Cn minus, so it's therefore acting as a weak acid. So in acid-base terms, it's the conjugate base we're after as our nucleophile. So if we start with a simple aldehyde, something like ethanal, and remembering that the C double bond O is polar, that means that the lone pair on the nucleophilic cyanide ion will be attracted to the carbon that's slightly delta positive. Normal nucleophilic addition, the pi bond in the C double bond O breaks. So seeing as the HCN was created in aqueous solution, you can either have the H plus, that is part of the dissociation, or you could have the water that's part of the solvent. So it could either be an H plus or an H2O that could be attacked in stage 2, the middle stage. So you'll notice that the final product, which I've drawn, is called a hydroxynitrile. It's got a hydroxy group, the OH group, and it also has 4 different groups coming off the carbon, so the carbon in the middle is chiral. So this compound will be called 2-hydroxypropane nitrile. Okay, just to recap as well, I've just annotated the mechanism there to say that in the second stage you could also be drawing it with water. If you do draw it with water, please make sure you put the dipoles in, because that's an important part of the mechanism, and it also requires you to break the HO bond within water. So now let's have a look at the nucleophilic substitution of nitriles. So this time let's start with something simple like chloromethane, for example. So you'll notice that the nucleophile attacks from behind because the partially negative chlorine atom would repel it. So it goes around the back a little bit like it did in the previous screen for similar reasons. So in the ethane nitrile product that you have, we have a new C-C bond. And it's important to point out that a new carbon-carbon bond is made irrespective of which of the two nucleophilic mechanisms the cyanide ion undergoes. So nucleophilic addition or nucleophilic substitution, both will create a new carbon-carbon single bond. Now it's also important to put the reaction conditions in. We use potassium cyanide or sodium cyanide dissolved in ethanol, not water this time, as water is a nucleophile and could interfere with the reaction. So there's 2 reactions of nitriles that you have to remember for your specification. First one is reduction using nickel and hydrogen gas. So we'll start with ethane nitrile and we'll add 2 hydrogen molecules to it using a nickel catalyst, which turns it into propylamine. You can see where the hydrogens have been added on as I've colour-coded them in blue. So let's take the same molecule again and hydrolyze it. So for this one you have 2 water molecules and 1 acid molecule. In this case we used HCl. That gives us a carboxylic acid with the same number of carbons in its chain length as the original nitrile. So ethanoic acid comes from ethane nitrile, and the side product is an ammonium salt, this time ammonium chloride. So you're probably familiar with the Friedelcrafts alkylation reaction using a halogen carrier. So R is any particular alkyl group. So as you probably recall, we create the electrophile using AlCl3, and then that can attack the benzene ring. And what's happened is, upon substituting CH3 onto the aromatic ring, we've created a carbon-carbon bond. which is now highlighted in the graphic at the top of the screen. And obviously you'd have to show an equation to show how your catalyst, your AlCl3, was recreated. So the H plus that comes off in the bottom right hand corner of the screen is what the CH3 is substituted for on the aromatic ring. So this is called Friedelcrafts alkylation. Let's look at Friedelcrafts acylation now, which is slightly different but in some ways very similar. So this time we'd have a different electrophile, and a really important additional condition here is anhydrous, absence of water, because the reagents, your acyl chloride or your acid anhydride that you've got there, will undergo reaction with water. Nucleophilic addition elimination will be the mechanism. So just taking the acyl chloride, for example, the acid anhydride would do a very similar thing. It would react with AlCl3 to make AlCl4-, and what would happen this time is that you'd get an acyl or an acylium ion. And this would also go on to react with a benzene ring via electrophilic substitution to produce an aromatic ketone like this. And in the same way, you're creating a new carbon-carbon single bond, which again we've highlighted. Okay, so it's time to try a simple question, or set of questions on this. So this isn't an exam question as such, it's just a worksheet I found, but it might be useful to have a look at it and see how this fits into maybe a broader multi-step or organic synthesis sort of series of reactions. Okay, so this is a simple series of steps which takes you from an alkene all the way through to a diol. Sorry, I beg your pardon, a dicarboxylic acid. So the first thing I've done is I've deduced what Z would be, because it says the conditions used for step 1. Obviously you need to work out what Z is so you can try and deduce what reaction conditions to apply. From an alkene you can get a dibromoalkane, because you can tell this because there's bromine being used. You get a dinitrile in step 2, and in step 3 the dinitrile is hydrolyzed to a dicarboxylic acid. We've covered that in this clip, so that's why I'm able to talk it through fairly quickly like that, hoping that obviously in the context of the clip it'll make sense. So the conditions used for step 1 would be use of aqueous bromine water, room temperature, and for the third mark I would probably suggest no UV light to prevent the formation of bromine radicals. It's a slightly odd question that it asks you for 3 things. So the presence of bromine radicals would undergo a completely different type of reaction, and it wouldn't undergo this particular scheme at all. You'd then get into free radical substitution, all sorts of things like that, which we're not interested in at this particular point. It's asked you to name the product Z of this reaction. We've already worked out that it's a dibromoalkane. So dibromoethane, 1,2-dibromoethane would be the one to be looking for, because the bromine adds across the carbon-carbon double bond. So carbon 1 and carbon 2 would both have a bromine atom attached and added to them. Okay, so bringing the sheet down a bit. It says, give the reagents and conditions required for step 2. So just bring it down slightly. There we go, so we can see step 2. So we'd warm it with excess KCN or NaCN in ethanol. And step 3 could be achieved by hydrolysis. And like we looked at earlier, you heat or reflux with dilute acid to achieve the hydrolysis under acidic conditions. Okay, so let's move the page down a bit further and see if we can get this last bit. So what I've done is I've drawn out my starting material at the top and my finishing material at the bottom. So this is an organic synthesis pathway they're trying to get you to do for 5 marks, so it obviously requires a bit of detail. The detail would be correct balancing, correct reaction conditions, and correct steps in the correct order. So the first thing you'd do is you'd brominate your buta-1,2-diene. So you're looking to add a bromine atom in 2 different places. Because it's a diene, each individual C-C double bond only has one bromine added, so for this reason you need 2 moles of HBr. Now you've got a 2,3-dibromobutane. This can be reacted with KCN, potassium cyanide and warm ethanol, to give you a dinitrile. And the dinitrile can be hydrolyzed so that at the point the nitrile group is substituted, carbon 2 and carbon 3, you get a COOH group instead. So this creates your 2,3-dimethylbutanoic acid. We use reflux and dilute HCl. So let's have a quick look at where the marks will come in here. So 3 marks for each correct condition, and the remaining 2 marks for the correct products that you get along the way during the course of your synthesis. So hopefully this has been a fairly useful clip in showing you how we can add carbon-carbon bonds to both aromatic rings and to alkyl chains that exist already using the nitrile functional group. It also takes you through how this can be taken into the context of multi-stage organic synthesis, which is the kind of skills you'll be able to need to have for the end of your course. So taking into account all the organic chemistry that you've done so far and how nitriles fit into that in terms of creating new carbon-carbon single bonds. So if you've got any questions, obviously come in to see one of us in a subject extension, or maybe bring them into your teacher. But in the meantime, thanks for your time and see you soon.